Hello everybody, I'm Alex. I mostly work on birds, and so in this presentation I'm going to be talking about wings, specifically focusing on what wing shape can tell us. So Britain is actually home, among other places, its range is quite extensive, to a record-breaking dinosaur. And it is the largest extant flying dinosaur. It's also renowned for its bad temper and its ability to hurt people. It can break your arm with a blow of its wing. So yeah, the biggest males tend to reach about 15 kilograms. One extreme specimen from Poland it reached about 23 kilograms. That was a absolute record breaker. And it is known as the mute swan, Cygnus olor. So yeah, here it is the heaviest living flying dinosaur. Or living flying bird, if you want to be slightly more technical. That is slightly disputed, because there are a few other contenders for the title. So recall that swans tended to reach about 15 kilograms. That's also true for trumpeter swans, which are the North American species. They tend to have slightly lower average weight, slightly higher average weight, but less of them actually reach the sort of 15 kilogram extreme mark. Similarly, great bustards, which are also native to Britain. There's been a reintroduction programme on Salisbury Plain. They were extinct in Britain for a couple of hundred years, but have now been reintroduced, which is great news. And their relative, the Cory bustard from Africa, also hit that kind of mark in the males. Females tend to be a lot smaller. And condors reach a similar kind of average weight of about 11 kilograms, which is the same as an average swan, though they don't tend to reach quite so many extreme heavyweights of 15 kilos or so. This is obviously really hard to tell because records aren't always good, they aren't always reliable sources, and it's hard to have verified records. So the 23 kilogram Polish swan is the record holder for heaviest verified flying bird. There are a few other contenders I want to mention briefly. So pelicans are usually a bit lighter, as are albatrosses. They tend to average about 9 kilograms, sometimes reach 11 to 13 kilograms. In particular, albatrosses, when they're taking off for the first time, tend to be very heavy because they've just had a lot to eat, and then when they have to go out and actually work for a living and fish themselves rather than relying off their parents, they tend to lose a bit of weight. This happens to a lot of people. I know it happened to me. Anyway, the interesting thing about all these birds is that they are completely different shapes. So from left to right we have the snowy albatross, the largest albatross species. We have a selection of pelican silhouettes, which is actually one of the best pictures I could find. We have a condor, and you can already see how from left to right they're really changing shape. So the albatross has really long, narrow wings with quite pointed tips, whereas these ones, so the pelicans, the condor, especially the condor, and the stork, they all have much more rectangular shaped wings. They don't taper anywhere near as much towards the tip, and they're much broader. And then we have, over on the far right, the swan above, and that's a great bustard below, and they have almost quite short, rounded wings. And that is reflected in the wingspan. So albatrosses have the highest wingspan, up to 3.7 metres. Pelicans come in a close second, though let's ignore that. Though their average figures are given here, so they're actually quite a bit smaller. 3.6 metres is unusually large. I've taken the maximum figure for each. Condors and storks are the sort of widest winged land birds, about 3 and a bit metres. And swans actually have comparatively short wings, despite being probably heavier than many of these, at only about 2.4 to 2.6 metres. So that is quite interesting because it shows you can get to the same kind of size of flying bird with really different wings. And indeed, these have all evolved their giant sizes convergently. They've all done it differently. So what does that different wing shape mean? Well, it's all to do with how they fly. So albatrosses use a technique which is known as dynamic soaring. So this is really interesting. They actually catch wind that is coming up off the waves, off the uneven surface of the sea, and use that to propel themselves. They're one of not many birds that do this. There are similarly shaped birds which also fly over the sea and soar, but they use thermal soaring. They use columns of air. We'll get back to them in a moment. They don't tend to be quite as big as albatrosses, so things like frigate birds, if you've heard of them. I'll show you some pictures in a bit. Similar land-based thermal soarers, you have these condors, the pelicans and storks to some extent. Pelicans and storks tend to use a slight mixture of flight styles. They also do gliding and burst flapping, sort of flap briefly for a bit and then glide for a long bit. Pelicans are also unusual because they often fly quite low over water and use a cushion of air, and herons do something similar. And then swans and bustards, because they have the shortest, roundest wings, they have to continuously flap to avoid falling out of the sky. If you've ever seen a swan taking off, you'll know that it's a lot of effort for them. They have to absolutely pelt across the surface of the water, flapping constantly. And bustards, they don't live on water, but similarly, they actually have to be really fast runners to take off. They can also outrun most of their floaters on land without flying. And they can reach about, I think it's about 50 kilometers per hour in a sprint, which is faster than humans. That's substantial. So, yeah, they're quite interesting. So much for modern birds. They all seem to top out at about 15 kilograms. What about fossil birds? This is a paleontology lecture after all. I ought to start talking about fossils at some point. So it turns out that weight is hard to accurately measure because you don't dig up a whole animal. It's not like finding a dead corpse in the rock. What you have are typically a lot of bones that have been mineralized, so you can't even get an accurate weight for the bones. They've been replaced with a different material. You might get some sort of imprints of soft tissue vegetation or cavity molds, but it's again very hard to tell exactly how big something was from that. And again, feathers don't tend to preserve well. You do get feathered dinosaurs in the fossil record with their feathers all preserved, and that is a great thing, but most of the time the feathers rot away or are dislodged from the body or just don't preserve because the rock is too coarse-grained. So in sandstone it's very hard to preserve feathers. You typically want mudstones or fine limestones. And this is a famous drawing of what we might interpret swans as if we'd never seen anything with feathers. So this was actually made in a book called Alter Days, talking about how a lot of dinosaurs were potentially inaccurately represented at the time, but I thought it served to show my purpose. So there are several kinds of giant extinct flying bird in the record, and they actually, some of the best examples do fit the categories I was previously talking about. So we have giant swan from Malta, Argentavis, which just means the magnificent bird from Argentina. Strictly speaking, it means the magnificent silver bird, but we won't fight about it. And that's basically a giant condor, we think. And then Pelagornis sandersi, which is what's known as a bony-toothed bird. We'll get on to the exact details of that in a moment. But for our purposes, we can think of it as pretty much like a giant albatross. I'll explain that in a bit more detail. So the swans. So they're known from partial fragmentary remains, mostly from the last few million years in Malta and Sicily. The weight is estimated to be about 16 kilograms as an average rather than extreme, so that's about 30 to 50% heavier than the mute swan. And you have similar extremely heavy specimens might reach 20 kilograms or so quite regularly. The wingspan, it's hard to tell because we don't have many feather imprints, but it's estimated to be about 3 meters based from the scaling size. Some studies do think it might be flightless. It would have had to be a continuous flapper like modern swans because it's just a scaled-up version. Here's the picture I was looking for. And yes, you can see it fighting the elephants. These are dwarf elephants, which were also found on Malta at the time. They would have been about as tall as these desks here, so about hip height. But still remarkably robust little creatures, quite heavy for something about this kind of size. But I wouldn't want to fight a swan that size, and nor do the elephants, really. So that might be about as big as a bird that has to continuously flap can get. It's certainly the biggest one we have a good record of. What about Argentavis? So that is known from, again, fragmentary material, sort of bits and pieces from across the body. So we have some bits of the arms, couple of bits of the leg. I think we might have some skull material referred. I'm not totally sure. That might be a different That might be a relative. So initial estimates, when they first found it, put it at weighing 120 kilograms and having a 7-meter wingspan. This is no longer considered accurate. It's since been downsized to have probably a between 5 and 5.5 meter wingspan, and that's still a lot bigger than a modern condor. Particularly when you account for that is an increase in one dimension, but it would have obeyed the sort of cubes law. So it didn't just sort of extend its wingspan. It also would be bigger, sort of nose to tail and head to toe as well. So it would have been bigger in 3 dimensions. The body mass is now thought to have been about 70 kilograms, is what current estimates suggest, which that does seem very high still. A lot. That's about 6 or 7 times modern condors. But it's plausible. It's not completely implausible because it did have a very large wing area. It would have had to be a thermal soarer. It was an inland creature. So here's some rather nice artwork. I think this is of the sort of original estimate rather than modern one, but it's such a nice picture I had to include it. And it's typically portrayed as a very large condor, because not all paleo artists are that imaginative. Those are some kind of saber-toothed, I think they're saber-toothed cats rather than saber-toothed marsupials, but I could be mistaken. The chins look like they might be marsupials. Anyway, I'm not a man of that. So yeah, there it is, sort of swooping down, and it would have driven things off their kills, rather like some vultures and condors do today, just by intimidating by holding out its huge wings. What about Pelagornis? Now, Pelagornis is an interesting one because it's part of a group that is totally extinct, called the bony-toothed birds. So as you can see up here, they actually have spikes coming out of their jaws. These are not teeth. Birds don't have teeth, at least not these birds. These are within the phylogenetic group that includes all modern birds. We're pretty confident of that, even if we're not sure exactly what they're related to. So they lack teeth. What they've developed instead is something a bit like some birds do have. So mergansers are a kind of duck which have sort of serrations along the bill, and that helps them grip slippery creatures like fish, which is what they eat. Pelagornithids took this to an extreme, though they're probably not closely related. They have these big spikes coming out of the bill. They would have been sheathed in the same kind of bill material. It's not just bone spikes. So it just had a very sort of spiky, tooth-like bill. And it would have used these for hunting fish as well, we think, based on the shape, size, and where they were found, which is typically marine and coastal sediments. So the Pelagornis sandersi is largest of several species in its genus. It has the bone spikes lining its jaws. Pelagornis sandersi is known from fragments, but because it's the largest species in its genus and it's not the only one, some of the smaller species, like Pelagornis chilensis, that is known from an almost complete, really well-preserved specimen. So a lot of bird fossils, because birds have hollow bones and quite lightweight bones to reduce their weight for flying, they tend to flatten when they're preserved, which is remarkably annoying. Pelagornis chilensis isn't particularly crushed or flattened. It's known from some really nice 3-dimensionally preserved bones. And scaling up from that well-preserved specimen to the material we have of Pelagornis sandersi gives it a wingspan of 6 to 7 meters. We're not totally sure because we don't know how long the feathers at the tip of the wing were. There isn't any feathers preserved from other Pelagornis. There are some from this part of the wing of a close relative Osteodontornis, which just means bird with bony teeth, because never let anybody tell you paleontologists are very imaginative all the time. We're only imaginative some of the time. So we don't exactly know what its wingspan was, but it would have been big. And in the body mass, there's a massive range of estimates from 21 to 41 kilograms. And that's a twofold difference. It's not agreed on what Pelagornis weighed. I have my own opinion, and we will get to this one in a moment, and I will promise I will back it up with maths. It's sometimes thought to have been a dynamic soarer. Other times it's thought to have been a marine thermal soarer, like the frigate birds I mentioned earlier. So here are a couple of photos of it, pictures. So this art has sort of portrayed it as, again, very albatross-like in coloration as well as in shape. This one has ignored the colour, but these two birds up above it that is a condor and an albatross. The little scale bar here is 1 metre. So that is a really, really large bird. So much for Pelagornis. And you can see that we have one continuous flapper in the group of birds we looked at, one land-based thermal soarer, and one marine soarer of some kind. And they all have very differently shaped wings, which is good. So let's talk about the size of these birds, because they all seem to have weighed more than that sort of 15 kilogram limit that we thought we had from looking at modern birds. What's limiting the size of a flying bird? And there are quite a few forces acting on a flying bird. Flying is really complicated and difficult, which is why vertebrates have only evolved to do it 3 times in birds, bats, and pterosaurs. So one thing that limits flying is muscle leverage and the length of the muscles. It's much harder to flap with a long muscle because you need to pull it an awful lot further to get a decent lever, and because there's much more resistance to pulling a long wing than there is a short one. So if you try to open a door by pushing near the hinges, it's going to be difficult, and birds can't really open a door or do the equivalent by pulling on the end of the wing, because then they'd have to have so much muscle involved that it wouldn't make a good gliding surface. The other thing that limits them is how heavy these muscles are for how much force they can provide. So swans and continuous flappers, for example, have very deep keels on the chest and a lot of muscle there, which is why we like to eat turkeys and ducks and chickens and geese and such like things, because they're covered in meat, and meat is tasty, I'm told. Another thing that limits the size of a flying bird is how heavy it is for the area under its wings. So wing loading is a measure of how much weight there is per unit area of a bird's wing, and the more weight there is, the more sort of lift you have to provide per area wing, or it's going to fall out of the sky. And birds do not typically want to fall out of the sky. There are some exceptions, such as plunge diving gannets, which fall out of the sky headfirst into the water and catch fish that way, but they then go back into the sky, so I don't think it counts. Another thing that limits flying birds is carrying around their weight on the ground. So there are some heavy birds that just do walking, like an ostrich, but walking requires very different muscles to flying if you're a bird. Birds fly solely with their arms. They don't use their legs to fly, and they don't use their arms to walk. They walk only on 2 legs, which means that they need 2 totally different sets of muscles, and therefore heavy things, depending on whether they're walking or flying. And they can't really get rid of one for the other, because birds need to be able to both walk and fly, which is another thing that acts as a weight limit. And takeoff is the hardest thing a bird has to do, because it's switching from walking around on those legs to flying. And that's really difficult. So to take off, a bird has to get itself high enough into the air that when it flaps, its feathers do not hit the ground and break. And like I mentioned, swans have to run really fast along the surface of the water, making lots of little flaps to do this. Other things like condors often launch from cliffs, which helps them avoid some of the problems of takeoff. Albatrosses catch the wind and do similar on their little isolated islands in the Southern Ocean. But yeah, takeoff is the most difficult thing birds can do, because they can't use their wings to push themselves up off the ground initially. They have to use their legs, or something similar. And then they can't use their legs to start flying. We'll get on to something that wasn't quite so limited by takeoff in a little bit. And here's some stuff talking about wing loading. We can skip most of it, but broadly speaking, Pelagornis, despite having longer wings than Argentavis, we think it had less wing area. That's certainly true for comparable modern birds. So albatrosses have a lot less wing area, and therefore a lot higher wing loading, a lot more mass per wing area than condors do. So they have to work harder to stay up. dynamic soaring tends to be a lot more difficult and complicated than thermal soaring does, we think. So we saw there was a lot of dispute over how heavy Pelagornis actually was. So I thought I might show you how we do these estimations of a bird's mass, and then we can get on to what it all means. And also, this is going to be very informative, I hope. So birds walk on two legs. This shouldn't come as a surprise to anybody in the room. They're theropod dinosaurs. As far as we know, all theropods were bipedal. There's been some argument about Spinosaurus. It's not a bird. We could ignore it for the moment. That means that a bird needs to be able to support its own weight while walking. It also needs to be able to support its own weight while flying, but that means the femur is the thigh bone, and obviously when you're walking on your legs, your thigh bones have to take a lot of the weight. Particularly when you're walking on two legs, because you have to lift your feet off the ground to walk, that means that at any given stride, one femur is going to be taking all of the weight of the bird. So similarly, flying birds have to be able to support their own weight with their wings, which means that the shoulder and the arm should get bigger as the bird gets heavier. So here's a picture of a bird skeleton. The femur is just here, and we can actually see that in birds, the femurs tend to be held closer to horizontally. Humans are straight bipedalism. We basically use our legs as pillars. Birds are crouch bipeds. They hold their legs slightly forward, so their centre of mass isn't, because they have really short tails, they have to hold their legs slightly forward so that the centre of mass is above the feet, otherwise they'd fall over. And that means that one of the major forces acting on the femur is bending force, which means that the femur is supposed to scale really tightly with body mass. That's not quite as true as people think it is in some respects. I'll get onto that in a moment. But yeah, things should scale with body mass, particularly the shoulder joint, the arm, and the legs. And those are often bits that are found reasonably well preserved in fossils. There is a large data set of extant, that is living, bird measurements and body masses, and the thing about a living bird is that it's quite easy to measure it. You just sort of pick up the living bird and put it on scales. Actually, you typically do it with dead ones because they don't try and fly off the scales. So these measurements include the sort of size of the shoulder joint that the upper arm bone fits into, the diameter of the humerus, the upper arm bone, and various measurements about the femur. These are the ones that are going to be important for our purposes when we're trying to estimate Pelagornis' mass, because there are also equations relating how big these measurements are to the body mass of the bird they come from. We have very good bones from Pelagornis chilensis, as I mentioned, and therefore we can estimate its mass pretty accurately, or we should be able to, if these equations hold, and then we can scale up to the slightly larger Pelagornis sandersi. There won't be any maths in this presentation. The maths is all going on behind the scenes. There is a lot, I promise. It's quite well backed, but I couldn't face presenting on it. I've already done it. So, here is a rather nice skeleton of Pelagornis. I think this is actually Pelagornis mauritanicus, a different species again, but they all look fairly similar skeleton-wise, so it'll do for our purposes. And this is one of the most well-presented skeletons in my view. It looks great hanging from the ceiling. So, the initial description of Pelagornis chilensis estimated its weight at the unhelpfully vague 16 to 29 kilograms. But they weren't really sure. So, from the femur length, the equations suggest it weighed about 12 and a bit kilograms, which is lower than you might think, considering how much more wing it has than an albatross, which doesn't weigh that much less. So let's have a look at some other measurements. From the femur width, 21.7 kilograms. That's a bit of a difference. From the femur circumference, and yes, those are two separate measurements. Width is just sort of straight across the femur, circumference is all the way around. It scales to 19 kilograms. The reason it's slightly different is because bird femora aren't always perfectly circular. They can be sort of oval. And so it's hard to know exactly which bit to take as the measurement. So these two agree reasonably well. There's a degree of uncertainty in all of these, so sort of plus or minus maybe 2 kilograms for each one. If these two are within about 2 kilograms of each other, so broadly speaking, femur width and circumference agree. From the shoulder joint, we have an estimate of about 33 kilograms, which is a lot higher than any of the others, and if we look at how thick the upper arm bone is, it estimates it to be 52 kilograms in mass. This is not helpful. This was so unhelpful, in fact, that when I did this, I then went back and checked every single bit of my maths to see if I'd made a mistake somewhere. And then I found that I hadn't, and that something else was going wrong. Which is both reassuring that I hadn't made a mistake, and concerning that something else is going on. But interesting. That's the important thing when you're doing science. The most important words in science aren't eureka, they're, that's funny. Because it indicates you found something new. And that's always a good thing. So these are all estimates for Pelagonus chilensis. Pelagonus sandicis is probably about 10 to 20% heavier. But chilensis has a better skeleton, so it's the one I was using. So in fact, yeah, scaling doesn't rule. There's something else going on. There are 3 possible options. Firstly, the scaling equations are wrong, despite the fact that they're based on a pretty large data set of modern birds. Secondly, Pelagonus's weight was on the heavier side of the estimates we've got, and some of its bones, in particular the femurs, are too small. Or thirdly, Pelagonus was on the lighter side of the estimates we've got, and some of its bones, the shoulder and arm, are too big. I mean, one of these has to be correct, because it has to be somewhere within the range of estimates we have, probably, unless it's doing something completely different. And in that case, at least one of the scaling equations has to be wrong, because they can't all be right, because they're giving different answers. We can also be completely sure Pelagonus chilensis is all the same individual. It's not like we're taking some bits from a small Pelagonus and some bits from a large Pelagonus and getting different answers for the mass, because then we'd expect to have different answers for the mass. But it's known from our fairly well articulated skeleton. It's all the same individual bird. So what I did was start asking why the equations might be wrong. This was not actually part of my brief at all. So this research that I'm presenting here is something I did very much as a side project because I got distracted while doing my master's, which was also on birds but on a different thing, and isn't really as interesting to a general audience. I might think about it at some point, but not today. Firstly, not all birds are the same. I mean, we saw that in the first few slides. Lots of flying birds look different. There are lots of ways to be a really big flying bird. Let's have a look at what we've got. So when we're using data just from marine soarers, so albatrosses, the frigate birds I mentioned, and a few similar things, that gives a very different femur length regression equation. And Pelagonus chilensis' mass estimated from that comes out about 25 kilograms, which is much more in agreement with the other bits of the femur. So possibly it just had short, but still quite stout femora. That is the technical plural of femurs. Don't worry about it. These equations also underestimate albatross weight. It turns out when I was looking at the dataset, they didn't include any albatrosses or condors in the sampling, which means it wasn't as helpful for my purposes as I'd originally thought. I'm trying to have words with the guy who made it, but he stopped responding to my emails. He was also my supervisor, so this is also a problem for several reasons. But never mind.
Dan.
It is Danfield, yes. Yeah, the data for the shoulder joint doesn't include any of these large marine saurers. The closest we've got is petrels, which are like albatrosses, but about this kind of size. So the ones I used for this new marine saurer length equation are albatrosses and their relatives. These are the frigate birds I mentioned. And then this here is a tropic bird, Phaethontiformes. There are only about 2 or 3 species of these, and they've converged on the marine saurer lifestyle independently. They're also a lot smaller, which is really useful for size regression analysis because it gives us a nice long line of points to work with, rather than having all the same kind of size. You'd expect them to be all sort of in a cluster on a graph. If you have a spread of weights and a spread of sizes, you can get a good estimate of the gradient of the line, which means you can extrapolate to something that's Pelagonist-sized without having a Pelagonist-sized bird in your sample, which is good because there aren't any. The other option is that it was on the heavier side, and some of its bones are too small, in particular the femurs. So if it was that heavy, and its femurs were that small, and then they shouldn't really be able to support its weight. It would actually struggle to support its weight without its legs snapping, which obviously isn't a good thing if you're trying to waddle around on land. So it would have had to push itself around on its belly, pretty much, using its legs as sort of paddles, from flailing against the ground. And that would have made takeoff even more difficult than it already would have been for a bird that had 3-meter long wings. Like, that thing wouldn't have been able to leap 3 meters into the air and flap. It would have had to take small flaps to start off with, or launch from a cliff or something, even if it could stand up, which, in my view, it probably could. I think the femurs are a better estimate, particularly given that the length estimate I've made brings it much more in line. And it was somewhere in the sort of low 20 kilogram region, so 20 to 25. But that is not yet published or discussed, so don't take that as a fact. See, responsible paleontologist. The other option is that its mass was in the low range, i.e. the femur equations are correct, this is the one I like, but that means that some of its bones are too big. So its shoulder joints are built for a 33 kilogram bird, its upper arms are possibly built for a 50 kilogram bird, which shouldn't be possible for other reasons, but we'll get back to that. So why might that be? So it could be due to sampling of taxa. Similarly, there are no albatrosses in the shoulder joint dataset. And why might its shoulder joints be bigger than we expect? So it could be just because things have to work differently at large sizes. Things don't always scale in a straight line when you're increasing size. Just because area is a square is up to the power of 2, but volume and therefore weight are to the power of increased to the power of 3 as you scale something up. The square cube law is a harsh master. Alternatively, what I think might be going on is that its wings appear to be too big because of how it used them. It spent nearly all its time on the wing. It was able to lock its wing joints in place, because if it's holding out its wings like this constantly, that starts to require quite a bit of muscular effort. Even if the wings are being held up by the wind and are what's supporting it, that still gets quite difficult to hold for days on end, which it would have been able to do. It would have been able to cross oceans, same as an albatross can today. They have a specialised wing locking mechanism. I think something similar is going on here, but because I don't have data on the albatross shoulder joints, I can't be certain of that yet. So this is currently a hypothesis. So that's about where we've got to. What have we learned from extinct flying birds? Well, we've learned that modern swans and bustards may well be approaching the limit for continuous flapping in a bird. The larger continuous flapper we have has been considered flightless in some studies. Narrow-winged soarers can probably get a lot bigger than modern albatrosses. Even the more conservative femur-based estimates for Pelagornis put it as several times the size of modern albatross, which makes sense given it has several times the size of wings. And modern condors are nowhere near as big as they could get. I mean, even if you take a more conservative mass estimate of 40 kilograms for Argentavis, which is probably on the low side, that's still a lot bigger than a modern condor for a broad-winged land-based thermal soarer. So the apparent 15 kilogram maximum from modern birds isn't genuine. It seems to be more of a coincidence that all our different kinds of birds that are flying today are like that. Can we learn anything else from this sort? Well, yeah, we can potentially use it to inform us about pterosaurs. Now, pterosaurs are really hard to understand because they are all extinct, which is a great shame. Some of them, not all of them, but some of them, are also much larger than birds, so potentially interesting for that respect, because we're pretty sure they still flew. They walked on all fours, so they didn't just have their wings hurled up like this, like a bird does. They walked on very long, powerful arms, and that means they could launch themselves off the ground. Let me find the picture. There we go. They could launch themselves off the ground using all four limbs. So this is actually a rather nice drawing because it's been used to show the stages of what we think a pterosaur launch would have been like. This is one of the biggest species as well. So it sort of rocks back over itself, pushes up with its hind legs, and then pushes with its front legs as well. That gets it high enough into the air, according to quite a few biomechanical models as well, that it can bring its wings up and over and flap and get into the air, even for a very large pterosaur, because they were sort of very long and quite lightly built. It's difficult to estimate the mass because, unlike birds, where we have a good living data set, or a living data set at least, we don't have any living pterosaurs that we can take a whole dead pterosaur and put it on the scales. This is a pity for a number of reasons, though actually considering the size of some of these, it's probably still true. Did pterosaurs have a similar range of wing shapes to birds? Well, this is another question that is really hard to answer. We don't know. Pterosaur wings are often less well preserved than bird wings even. Like, feathers are pretty tough keratin stuff. They're as hard as nails, well, fingernails, particularly the core of a feather is very tough. So they can sometimes preserve quite well. Wing membranes, they're made of softer, more flexible proteins. They preserve quite poorly. I'll see if I can find the picture. There we go. For some reason, I think the transfer from PowerPoint to Google Slides affected things. Anyway, I will not complain about technology. This is one of the best preserved sort of pterosaur wing membranes we have. This is Rhamphorhynchus in very fine-grained limestone from Germany. This is also the same limestone that Archaeopteryx was found in, so it does also preserve feathers as well. And we can see that that has sort of long, narrow wings. What we're not quite certain of is how far the membrane extends down the leg. So because the wings are supported by a single large finger rather than a sort of stiff row of feathers or multiple fingers like a bat, it's hard. One of the major things that affects the shape and area of the wing is whether it goes from fingertip to hip, or from fingertip to knee, or from fingertip to ankle even, because that will give you very different overall shapes of wing. And if anybody here has seen Prehistoric Planet, you might have noticed that in that reconstruction, the big Azhdarchids, the giant pterosaurs, hold their legs quite a way out to the side while they're flying, whereas in other reconstructions they're often drawn as having their legs sort of pointing backwards. And that massively changes the overall shape of the wings we end up with, the wing membrane. So we can't be sure about pterosaur wing shapes. There's a lot of estimation going on, and a lot of paleo art, I think, doesn't draw enough membrane in. There's even been some recent work which suggests that a lot of the official plan forms used, which are effectively sort of a picture of a pterosaur like this and just a silhouette showing the membrane, a lot of them, all the wings look like they have the same shape, even in proper scientific publications, which is potentially concerning. However, we're scientists, we're going to try and learn stuff about them anyway, because it's what we do. So, first group we're going to talk about are pteranodontoid pterosaurs. There will not be a quiz later. This is a rather nice picture of one. So this is Pteranodon itself. They have very long wings and lightweight bodies. You can actually see a skeleton of a reasonably small Pteranodon outside in the stairwell at the top, so have a look at that on your way out. Mass estimates typically give more than about 30 kilograms, even for the largest ones, but they had a really long wingspan because of the very, very long single finger, which is as thick as the rest of the upper arm. So the biggest ones like Pteranodon and Tropionathus were possibly up to somewhere in the 7 to 8 metre range. And we can actually get a rather better estimate for direct wingspan from a well-preserved specimen than we can for a bird, because it's bones supporting the wing all the way to the tip rather than feathers. So it's quite a fragile bone, but it does have a slightly better preservation potential than feathers. So they, based on the shape of the wings, which we're fairly confident had to be fairly long and narrow because they have short bodies. Even if they hold the legs out all the way to the back, they can't have that broad a wing because they've got only very short legs. So they would have had to be long, narrow wings, and based on that and their where they've been found and the fish remains found in their gut, some of them, and also some of them have clear adaptations for eating fish. They are thought to be long-distance marine soarers that ate fish similarly. Again, there's dispute over whether they were dynamic soaring like an albatross or thermal soaring like a frigate bird, but that's true for pelargonids as well. They are very, very comparable to giant pelargonithids in a lot of respects. So size, weight, wing shape, and in even ecology. So that is potentially quite a useful thing to know. However, so these are relatively comparable to some of our extinct birds, and therefore not too far removed from some of our modern birds. They would have taken off from all fours, which is possibly why they might have been able to get a bit bigger than Pelargonus, but and they were quite differently shaped, so they had a lot more skull and a lot less body. Particularly if you look at that one, it has its very big dramatic crest. But there are some groups of pterosaurs which aren't so easily understood by comparison to modern birds because they are well outside the range of what we see in modern birds. So these Ajdarchids, I can't remember which one exactly that's supposed to be a picture of, but these... I'm impressed you can get it from the picture alone. Thank you. Oh yeah. But yeah, these ones, I mean, you can see the wing membrane is reconstructed as being pretty tight to the skin there, which, again, is potentially a bit dubious because we don't have, I don't think, any really well-preserved wing membranes from Ajdarchids. They were so big that you don't often get, and they hadn't evolved by the time that really fine-grained limestone we have the Rhamphorhynchus from was being laid down, I don't think. Certainly not the giant ones. They were the largest flying animals ever, by some way. So probably most of you have heard of Quetzalcoatlus, it's the really famous one. There were others, some of them more heavily built, if not necessarily larger winged, particularly more robust in the skull and neck. Quetzalcoatlus seems to have been quite a long, thin member. The wingspan was up to 11 metres, we think, debatably. But that's on the large estimates. But even allowing for a bit of doubt there, still well over 9 metres, which is much bigger than any modern bird. And the weight, the mass estimates are currently at 200 to 250 kilograms. It seems to be reasonably in agreement, which is much, much heavier than any of the modern birds or extinct birds we've been dealing with so far. So what do we use as a flying model for that? The answer seems to be the best thing to do is look at the wing loading. And the wing loading is not great. Because they're so heavy, even though they have potentially really huge wings, there's a lot of mass per unit area. It takes a lot of effort to keep them up in the air, which is possibly one of the reasons related to why they seem to be so terrestrially capable. We have some good trackways from Ajdarchids or Ajdarchid relatives, and they're generally now thought to have hunted and spent most of their time walking around on the ground, and only flown when it was very necessary. So a recent study from I think 2022 suggests they were continuous flappers and paw soarers. Even though the wing shape is uncertain, there's just a limit to how much area you can fit in, no matter what the wing shape was. You would have had a high wing loading. So that is interesting because it's much, much bigger than the previous largest continuous flappers we've seen from birds. So that suggests that quadrupedal takeoff really is important if you're a continuous flapper. And that might be because if you're using similar muscles to push off with your arms and to fly with your arms, that's much more efficient than having to leap with back legs and fly with arms. So you can use more of the muscles for the same thing. If that makes sense. It's also just they could get themselves higher because they're effectively, you can see how long these are. This is potentially up to about 2 and a bit meters off the ground. They're using that as a pole vault to get themselves into the air. And yeah. So, pterosaurs, we're still not totally sure about them because we don't know what their wing shape was, not well. But we can still make some educated guesses from looking at body mass and just how much wing you could possibly fit on there and the range of estimates, which is useful. So having that sort of wing loading knowledge from birds is a really useful thing to have. What do we learn from those pterosaurs then? So this is a really nice figure from the paper I was mentioning that talks about the flight styles. It's a nice figure partly because it has very clear demonstrations of what it's meaning. It's also just got really nice pictures of all the flying creatures, and I like them. And they're all to scale, which, yeah, it's a good slide, it's a good picture to start this talk with. And we can see the magnificent frigate bird, that is actually its name. There are 5 species. There's the Great, Ascension, Christmas, Lesser, and Magnificent frigate birds. I may know too much about birds at this point. You can see it's still got a pretty decent wingspan. It's not quite comparable to the albatross, but it's still big. It's particularly big for its weight as well. It's a very lightweight bird. So across a couple of different groups, so pteranodontids and pelagonophids, we seem to hit the same kind of 30, maybe a bit more limit in dynamic or possibly thermal marine soaring. So that may be a genuine limit. It was initially, when Quetzalcoatlus was dug up, it was thought to be something similar, but we now know it was completely different based on a lot more, a lot better understanding of Astarchids. Yeah, that seems to be a genuine limit, which is again much bigger than what we have currently at the albatross. So for that kind of soaring, the quadrupedal launch doesn't seem to make that much difference in how big you can get. Pteranodon and Pelagonis are not too dissimilar in size. In terms of continuous flapping, on the other hand, the biggest birds here represented by a bustard rather than this one, but we can pretend it's the British Great Bustard if it makes you feel better. That seems to make a massive difference for how big a continuous flapper or a very poor soarer can get. And similarly, those both very terrestrially capable. The bustard and the Quetzalcoatlus are both very terrestrially capable. They find all their food by walking for it, though bustards don't tend to hunt quite as much as we think Quetzalcoatlus did. And they use the flight to get out of trouble and to travel to new places, typically quite close ones. As for very large thermal soarers, we don't seem to have found that many very large land-based thermal soarers with wings shaped like these. There don't seem to be that many pterosaurs that have wing shapes like that. Possibly that's because of how we're reconstructing them. We might be not putting enough membrane on. But possibly it's just because if you're only supporting the membrane from wingtip to somewhere on the body, you have to have a pointy end of the wing. That is still up for debate. So, what have we learned? Is that wing shape makes a massive difference to how something flies. So if something has long, narrow wings, it's really good at flying over water. Fairly long, broad wings, it's very good at soaring over land. And then pelicans and storks and things like that are sort of intermediate. They're quite good at most types of soaring. Which is why they spend some time over the water, unlike condors. And then shorter, more rounded tipped wings like swans and bustards are much worse at soaring. They have to flap continuously. Broad-winged terrestrial soarers might have a higher size limit than what we see today. We're not sure how Argentavis took off. Because it's not known from a complete skeleton, it's quite hard to model that biomechanically. Um, Probably similar to condors, it would have had to use cliffs to launch itself. The conclusion: we don't fully understand pterosaur wing shape. There's some uncertainty about how they flew, but we can still make some reasonable inferences about it. And finally, yeah, there are many ways to fly. All these things evolve giant size independently. So pterosaurs and birds are obviously completely separate origins of flight, but all of the birds we've been talking about, their most recent common ancestors were probably fairly small birds. Similarly, the common ancestor of pteranodontids and ashtarchids probably wasn't that big a pterosaur. I don't wish to name a figure. That, I think, is about all. But I hope you've enjoyed the presentation on wings, and maybe next time you see a bird flying, you'll appreciate it a little more. Because it's a difficult thing to do. Okay, here, this is now a different type of way of flying. So this is, I think, a microraptor. And you can see it actually appears to have 4 wings. The back pair are just its hind legs, which have long flight feathers on as well. We don't really know how those were used, but some early birds, like Archaeopteryx, are also thought to have had that kind of flight feathering on the legs. We don't know why modern birds lost. We don't know why later birds lost them. That is genuinely still a mystery, I think. We also don't really know what that would have done to its flight performance and centre of mass. It might have made it a much better glider, but worse at powered flight, for example. It would probably have made it more stable and less manoeuvrable in the air. But no 4-winged gliders have ever reached giant size, as far as we know, which is a shame. That would be very interesting. So thank you all for listening and coming along. I am very happy to take any questions, primarily about birds. If you have questions about pterosaurs, you might be better asking Brian. He knows more about them than I do. Yeah, are there any questions?
When swans take off from land, have they got to be on water?
I think they can take off from land, but they're not very good at it. It takes a lot of effort. It's also much more risky. So if you've seen a swan taking off on water, you might notice that the tips of its wings do quite often strike the water's surface. If you had that on land, that would really risk damaging the big flight feathers, which are very important for keeping the swan in the air, so need to not be damaged. So yeah, they won't take off from land unless it's a real emergency, which is partly why they're so aggressive. They need to be able to drive things off without taking off on land if they're limited to water takeoffs. Great. Yes?
Does a data set for albatross measurements exist, or is that something that you'd have to create to get?
There are other data sets which have some limb measurements for albatrosses. So how I got the different femur equation that I used for getting the 25 kilogram estimate of Pelagornis, that was a different data set which involved a lot of the lengths of bones, but didn't involve anything with the shoulder joint, and that included albatrosses, and that was much more thorough across all birds. So I like that one. But no, if I wanted to know albatross shoulder joints, I'd have to go and measure that myself with calipers and a lot of bones. Yes.
They all have like air sac system.
Yes. So both birds and pterosaurs have very thin, hollow bones. They do have some bone marrow, but most of it is replaced with air. There are currently studies going on as to how certain birds, like diving birds, which need to be heavier, have actually replaced that with marrow again secondarily. And not just diving birds like penguins, it's in quite a few seabirds. Yeah, we think that an air sac system that didn't invade the bones is probably present in the common ancestor of birds and pterosaurs, I think. But they evolved it sort of invading and hollowing out bones independently, which is why only some dinosaurs have that. So things like Triceratops and Hadrosaurs didn't have hollow bones, air-filled bones like that. So it's been used for flying, but in birds and their ancestors, it wasn't evolved for flying, whereas in pterosaurs, it probably was, if that makes sense.
How high could pterosaurs fly then? How high up in the sky?
So that is something that really doesn't preserve well in the fossil record, for obvious reasons. I really don't know, I'm afraid. Long distance soarers like pteranodontids probably could get fairly high. So frigate birds, I can't remember offhand, but they've definitely been recorded as getting to, I think, at least 3 to 5 kilometers up above the sea. So it's possible, and then they sort of just glide, losing height very, very slowly. They just glide for hundreds or thousands of miles further from that.
So can condors fly higher with the thermal?
Sometimes they also tend to start from a high altitude because they live in the mountains rather than over the sea, which helps. Often the highest flying birds are, there are some vultures and condors, which they all fly similarly. But I think some of the highest flying birds are actually migratory continuous flappers, like ducks and geese. Which, geese are just really good at continuously flapping for a very long way.
Thank you.
Cool.
I've got a question for you. So those shorter, broader wings that you see, like in our vultures,
Yes.
thermal soars, is there something about that shape that helps with the thermal soaring?
I'm not totally certain. I think part of it, the breadth certainly is to get as much surface area as possible, because it's a much more passive process than dynamic soaring. It tends to benefit from very, very low wing loading. In terms of why they tend to be slightly shorter, I think it might just be because they don't need to, because they get all their wing area from feathers. They don't need to put as much wing area resources into extending the bones as albatrosses do, and bone is very expensive to produce and make because calcium is quite a rare element around. So if a bird can get away with shorter wings, it probably will, because calcium is also used for the eggshells, and birds aim to maximise their reproduction. Same as everything does. That's the best answer I can come up with off the top of my head. I don't know. I am not that good at aerodynamics. I mostly just like birds.
Did pterosaurs fly to hunt, or was it just to get out of the way of something on the ground?
So probably like birds, there was a bit of variation in why any particular pterosaur would take off. We think the long-winged pterodontid ones hunted by flying over the sea and catching fish and such like, fish and squid and belemnites. In terms of actually hunting in the air, pterosaurs probably wouldn't have been as good at that as birds, because although they did have that wing membrane leading down their legs, we think, that actually means they couldn't have evolved hawking forms, so they couldn't have brought their legs forward to catch things in the air like modern hawks and eagles do.
If you want to see a good example of a pterosaur that has a hawk on the wing, you can find one in our bathroom. Over the
That is a
toilet,
good point.
there's a
Yes.
picture. It's called the fuzzy cute or fluffy cute pterosaur. A weird type of pterosaur. They're near gnathids. They hunted insects on the wing.
But yeah, they didn't hunt. They didn't hawk with their legs. They used their mouths more like a swift.
Has there ever been a bird that can fly more continuously than a swift?
I'm not sure. I think swifts may genuinely be the best at flying continuously. They are incredibly good at it. I do like swifts. Great.
Yeah, thank you for being the first of our internship lectures here. Alex is here as part of our internship program and has had the gumption and personal bravery to be the first to go of our folks. And thanks for coming and giving us